Modern games have a texture problem, and it is getting worse every year as developers push for more photorealistic graphics. The materials that cover every surface in a game world have become dramatically more complex. A single material that used to be just a color image now requires multiple layers of information working together. Consider what goes into a modern physically based rendering material. You need an albedo map showing the base color, which is 3 channels for red, green, and blue. Then, there is the normal map, which encodes surface detail and requires at least 2 channels, add metalness, roughness, ambient occlusion, and potentially opacity, and you are looking at 9 or 10 channels for a single material. Some materials push this even further, reaching up to 16 channels when you factor in additional detail, maps, and specialty properties. This multiplies quickly across an entire game. A character might have dozens of materials. An environment can have hundreds. Each of those materials needs all those channels at multiple resolution levels for proper mip mapping. The math becomes staggering. A 2000 by 2000 pixel texture set with 10 channels at 8 bits per channel consumes over 30 megabytes in raw form, and that is before you even consider the MIP chain. The traditional solution has been block compression formats like BC7 and BC5. These help, but they were designed for a different era. They compress each texture independently, missing the fact that all these channels are related. The detail in your albedo map often corresponds to detail in your normal map. The roughness variations frequently align with features in other channels, but traditional formats cannot exploit these relationships. This is the crisis that neural texture compression was designed to address. Game developers are caught between rising player expectations for visual fidelity and hard limits on video memory and storage space. Something had to change in how we think about texture compression because the old approaches were hitting a wall. The core of neural texture compression lies in how it fundamentally rethinks what a texture actually is. Instead of storing raw pixel data for every texel across dozens of material channels, NTC transforms everything into 2 components: a set of learned latent features and a small neural network decoder with its weights. The latent features are where the compression happens. Think of them as a compact representation that captures the essential visual information of your material. Each position in this latent texture stores a feature vector describing material properties rather than final color values. These feature vectors are dramatically smaller than the original texture data, which is where the memory savings come from, but compressed data is useless if you cannot get it back out. That is where the neural network decoder comes in. It is a small multilayer perceptron that runs on the GPU and reconstructs texel values on demand when a shader needs a texture sample. It feeds UV coordinates into this decoder along with the latent features, and the network produces the reconstructed texel value. Right there in the shader, there is a clever trick involved here. Standard neural networks can struggle with fine spatial details, tending to blur everything out. To solve this, NTC applies positional encoding to the UV coordinates before they reach the decoder. This injects high-frequency spatial information that helps the network accurately reconstruct sharp details and repeating patterns that would otherwise be lost in a compressed representation. The important thing to understand is that this entire process is deterministic. NTC is not a generative AI system that hallucinates new content each time you call it. Given the same inputs, the decoder produces identical output every single time. What goes in is exactly what comes out, just reconstructed from a much smaller storage footprint. Let us look at the numbers, because they tell a pretty remarkable story. A typical PBR material bundle with albedo normals, roughness metalness, and ambient occlusion adds up to 64 bits per texel when stored as raw uncompressed data. That is a lot of memory for a single material. Traditional block compression helps quite a bit here. You would typically pack the albedo into a BC7 texture at 8 bits per texel, put the normals into a BC5 texture at another 8 bits per texel, and combine roughness metalness and ambient occlusion into a third BC7 texture, also at 8 bits per texel. That brings the total down to around 24 bits per texel. Not bad. But here is where NTC gets interesting. Neural texture compression can achieve comparable visual quality at roughly 5 bits per texel. That is roughly 5 times more efficient than BCN, and we are talking about quality levels in the 40 to 50 dB PSNR range, which is considered visually lossless for most practical purposes. Now, there is an important philosophical difference between how these two approaches handle data block compression. Formats like BC7 and BC5 have a fixed data rate. You choose the format, and you get exactly that bitrate, no matter what the texture contains. NTC flips this around. It works as an adjustable quality constant bitrate scheme. You specify your target bitrate upfront by choosing what is called a latent shape, which is basically a combination of how many channels of features you store, their resolution, and their bit depth. The compression process then does its best to minimize reconstruction error. Within that budget, different latent shapes give you different bitrates, so you can dial in exactly how much memory you want to spend per texel. This gives developers real control over the trade-off between memory footprint and visual fidelity, rather than being locked into whatever fixed rate a particular BCN format happens to provide. The Tuscan Villa demo shown at GTC 2026 gave everyone their first look at what this technology can actually do in a real scenario. NVIDIA loaded up a detailed scene with all the textures you would expect from a modern game environment with traditional block compression. Those textures consumed 6.5 gigabytes of video memory. Then they switched to neural texture compression, and the exact same textures dropped to just 970 megabytes. That is an 85% reduction. And it happened in a scene that represents what developers are actually building today. Not some synthetic benchmark designed to make the numbers look good. What makes this demonstration particularly interesting is that developers have a choice in how they use that savings. They can take the straightforward path and simply reduce memory usage, which opens up headroom for games that push hardware to its limits, or they can flip the equation entirely. Instead of reducing memory, they can keep the same memory budget, but pack in significantly more detail than block compression would ever allow. The same 6.5 gigabytes that previously held standard compressed textures could now hold substantially higher fidelity materials without introducing the artifacts and color bleeding that plague traditional compression methods. The benefits extend beyond what happens on your graphics card. Smaller texture data means smaller game installs, which is becoming a real concern as modern titles routinely exceed 100 gigabytes. Patch sizes shrink accordingly. Download times improve for players with slower internet connections or limited storage. These downstream effects matter just as much as the technical achievements happening on the GPU. So how do developers actually use this technology in practice? The answer depends heavily on what hardware they are targeting. NVIDIA designed NTC with 3 distinct deployment modes, each serving a different point on the hardware spectrum. At the high end, where you have powerful GPUs with dedicated tensor cores and ample computational headroom, developers can use what is called direct shader decoding. This is the most ambitious approach. The compressed latent textures stay compressed in memory, and the neural network decodes them in real time, right inside the pixel shader or ray tracing hit shader. Every time the renderer needs to sample a texture, the shader pulls the latent data, runs it through the small neural network, and gets back the full material channels. The catch is that the decoder produces unfiltered data for a single texel, so this mode works best when paired with stochastic texture filtering. To handle the actual texture filtering, it is computationally expensive, but it gives you maximum memory savings because nothing ever gets decompressed ahead of time for games targeting lower-end hardware or platforms without strong neural processing capabilities. There is the inference. On load mode, this takes a completely different philosophy. When the game loads a level or a map, the NTC textures get decompressed right then and transcoded into traditional block compressed formats like BC7 or BC5. The neural decoding happens once at load time. Rather than every frame, you lose the ongoing memory savings during gameplay, but you still get the benefit of dramatically smaller install sizes and faster download times. The textures live on disk in their compressed neural form and only expand when the player actually needs them. The third option sits somewhere between those two extremes. It is called inference on feedback, and it is designed for hardware that supports sampler feedback, a feature that lets the GPU track which texture tiles are actually being accessed instead of decompressing everything or decompressing nothing. This mode builds a sparse tiled texture in video memory. As the camera moves through the scene, the system identifies which tiles are visible and decompresses only those specific tiles on demand. The result is a kind of middle ground where you get better memory efficiency than full decompression without the heavy per-frame compute cost of real-time. Decoding each of these modes represents a different trade-off between memory savings, computational cost, and hardware requirements. Developers can even mix them within the same game, using direct decoding for hero assets on high-end settings, while falling back to inference on load for players with more modest hardware. So where does all of this leave us in the real world? The SDK has been sitting on GitHub since early 2026, completely free to download. Yet, not a single game developer has publicly announced they are using it. That might sound concerning at first, but it makes sense when you think about the timelines involved. Game development cycles run for years. A studio starting a new project today might ship in 2028 or 2029. The technology is ready, but the games that could really showcase it are still being built. One interesting detail that often gets overlooked is that NTC is not an NVIDIA exclusive. The decoder runs just fine on AMD and Intel hardware. This is not some proprietary lock-in strategy. It is a genuine attempt to solve a problem that affects everyone making games. That open approach has fueled speculation about where we might see NTC show up first. The rumor mill points toward Sony, who reportedly are exploring the technology for PlayStation 6. The thinking is straightforward. If you can compress game assets by 85%, you can ship the same game on a smaller SSD. A 1 terabyte drive becomes feasible where 2 terabytes might have been needed before. That saves money on hardware costs and reduces download sizes for players. NTC also exists as part of a larger shift toward neural rendering. It sits alongside DLSS5 and something called neural materials, which compresses 19 material channels down to 8 and achieves render speedups between 1.4 and 7.7 times. These technologies are converging. the next generation of game engines will likely treat neural decompression as a standard part of the pipeline, rather than an exotic add-on. We are watching the early days of something that could reshape how games are built, shipped, and played. The adoption will come, it just needs time.